Hi, pre-calculus students. Welcome to the last section of chapter 10 on polar equations of conic sections. So what we've done so far is in sections 10.2, 10.3, 10.4, we looked at conic sections in rectangular form, in XY form. And then later in 10.7 and 10.8, we looked at polar points and polar equations. So now what we're going to do is bring those together and write equations of conic sections in polar form. Again, this makes sense for a couple of reasons. The first reason being that a polar graph is curved, and so are our conic sections, and so they fit the graphs well. And our world is round, as we say from the polar graphs. Also, it really kind of makes sense as far as parabolas, as far as projectiles, and ellipses as orbits, and hyperbolas as the way light and sound come out from a focus, that the focus and the source of the rotation in an orbit, or a source of light, or the source of waves coming in and out from a satellite dish in a parabolic form, that the focus is actually the center. When you think about it, when you have an orbit, right, like we are, orbiting around the sun, right, then the sun is actually the focus, and the orbit is around that focus, right? The center point at any time between the earth and the sun really isn't anything that we study or recognize in our real world. Same thing with light and sound. When you're talking about a hyperbola, that comes out or in, same with a parabola, from a focus, right? Not really from a vertex or a center point. So it's important to study the polar equations of conic sections. And it's also important for Calc 2. All right, so I'm going to go ahead and share my screen. As I know, I always say this, but I think this is kind of fun, kind of like treasure hunting, clue hunting. And I have some notes here for you. So pull out your chapter 10 notes. I did add some polar graphs that are not in your notes, so sorry about that. That was an afterthought. I'm like, oh, I could really use some polar graphs here. So no worries. You just use your own polar graphs, or you can just sketch without a polar graph. So everything I said here in bold, right? I just said in bold. And so here's what we need. Let's just jump down to number 2 really quick, and then we'll go back up to number 1. What is the basic form of a polar equation, right? So of course it has R equals, right? Because the input for a polar equation is an angle measure, right, theta, and the output is a radius, and that's the way we input them into our calculator. So for a polar equation of a conic section, and that would be for, we're going to study again, a parabola, ellipse, and hyperbola, we are going to use E, which occurs in the numerator and denominator. That is the eccentricity, right? We are going to use P, which is a distance from the focus or the pole to a directrix, and we'll be using a directrix. We will have a constant in the denominator of 1, and if we do not have that, we're going to need it. And there's a plus or minus, and we'll have a cosine of theta. So let's talk about what all of these variables and trig functions do. So let's go back up to number 1. Rather than graph conics in rectangular form or polar form, when the center of the conic occurs at a polar origin, again, as it does in the real world, there are many applications of conics where it is more convenient to use one of the foci as the origin, literally at the center of a polar graph, which we call the pole. And we consider the eccentricity the eccentricity, should have given myself more space here, of the conic along with the ratio, that's a fraction, from the focus and the directrix. So again, on number 2, we talked about a basic polar equation and what we see in it. So the E again, the E is the eccentricity. I can spell this, eccentricity. And then the P that you see in the equation, the absolute value of P is the distance from the focus to the directrix. All of these things are going to help us graph. The constant in the denominator must be 1 for us properly to read what E is. So if our denominator, if that first constant is not a 1, we can easily make it a 1. And then we can read our E right here. That is right next to the cosine or sine. So if you have a cosine of theta, that means the directrix is vertical and that your conic section has a horizontal orientation. But we really care about the directrix, that the directrix is vertical, because we're going to be drawing it. And if you have sine of theta, that means the directrix is horizontal. That means that the conic section has a vertical orientation again, but we're going to be drawing the directrix, and so we need to know that it's horizontal. If you have a plus sign before your trig function in the denominator, it means the directrix is to the right or above the pole. This makes sense, right? Because on our XY planes also, right and above means positive, right? If you have a negative in your denominator, that means the directrix is left or below the pole. Again, this is going to help us draw our directrix. Okay, if your E is greater than 1, and again, there is an E in the numerator and denominator, but we use our denominator to get our E, then you have a hyperbola. If your E is equal to 1, you have a parabola. And if your E is less than 1, then you have an ellipse. Okay, so now the E is not just the eccentricity, but it's telling us what conic section we have, and it's based on the ratio between the focus and the directrix. A vertex always lies somewhere between the pole and the directrix. Not necessarily halfway, but between the pole and the directrix. There we go. So how do I graph a conic section by hand that's in polar form? Again, I think it's kind of fun. First, we will determine the type of conic section we have by finding E. And so remember, we have to have a 1 in the denominator first. And then we read our E next to cosine or sine. Then we use the E times P in the denominator, the numerator, the E times P in the numerator to get our P. So our E comes from the denominator. Next, B, determine the location of the directrix by using positive or negative cosine or sine. So cosine or sine will tell us if the directrix is vertical or horizontal, and plus or minus will tell us if it's to the left, right, above, or below the pole. And then we'll find P from the numerator to find out how far. where the directrix is located from the pole. Okay, then the next thing we do is we find vertex or vertices and other useful points by using appropriate radian measures. So what we do is we make a chart. And our chart will have, usually all we need is theta and r. And we'll do a 0 radian measure, pi over 2, kind of went upward there, pi, and 3 pi over 2 is usually all you need to draw your conic section. Okay, let's try some examples. Okay, on number 4, we have a polar equation, r equals 4 over 1 minus cosine of theta. Now, first of all, we have to check our denominator to make sure that we have a constant of a 1. And we do right here. There we go. That means that our e is next to our cosine. That's an arrow right there. And it must be equal to 1. Okay. So the e is next to cosine in the denominator. So e must be 1 because that is the coefficient that's in front of the cosine if there's not one listed. So awesome. This means we have a parabola. Because it says on our sheet, if e is equal to 1, we have a parabola. Okay. Now we're going to need the directrix. So here's what I do. The directrix, I have to collect information about it. First of all, I have cosine, and so my directrix is vertical. Next, I check my sign, and I see I have a negative before the cosine, and so that means that my vertical line must be left of the pole, right? If it was a horizontal directrix, it would be below the pole. Now I just need to know how far, and that's what P is. Okay, so let's take a look. In our numerator, 4 equals E times P, right? When you look in the formula on number 2 in your notes, E times P is in the numerator, right? And we know that our E is 1. So our P must be 4. There we go. So the directrix, here's the pole, of course, at the pole. And our directrix is vertical and it is left 4. So it's at x equals -4. So even though we have a polar graph, we know that we can put an XY plane over the top of it, right? Here's our X and Y axis. And so my directrix would be located at 1, 2, 3, 4. I usually make it with a dashed line. There we go. There's our directrix. Okay, so how do we draw our parabola now? The next thing we do is we make a chart and then we draw the points. So here's theta and here's r. And we're going to look at a radian measure of 0, pi over 2, pi, and 3 pi over 2. That's a 3. 3 pi over 2. All right, here we go. So for a radian measure of 0, we put that into our equation. In the denominator, cosine of 0 is 1. 1 minus 1 is 0 in the denominator. And you may be like, uh-oh, I can't divide by 0. It actually makes perfect sense. Let's just put undefined for our radius. Pi over 2. Let's put that into our equation. Cosine of pi over 2 is 0. And so we have 4 divided by 1 is 4. At pi, cosine of pi is a -1. So we have 1 minus a -1 is 1 plus 1 is 2. 4 divided by 2 is 2. Let's do 3 pi over 2. Cosine of 3 pi over 2 is 0, and we have a 4. So these are polar points here that we are going to graph. All right, so let's record the point. We can't record 0 in an undefined radius. So let's go and let's record pi over 2 and 4. So let's go to our polar graph. We'll go pi over 2 and up 4. 1, 2, 3, 4, and make a dot there. See if I can make that a little darker. There we go. Let's do the polar point pi in a radius of 2. Pi in a radius of 2 would be here. Here we go. There we go. Make better points there. And then 3 pi over 2 and 4. So let's rotate 3 pi over 2 and 1, 2, 3, 4. There we go. So our parabola goes through these 3 points. As I said, the vertex is located between the pole and the directrix. Now you can see why the point 0 at 0 radians is undefined, right? Because at 0 radians here, there is no point for the parabola. So actually, that first point made perfect sense that we couldn't record it, right? Let's graph B. Okay, notice we first have to have a denominator. In our denominator, we need a 1 to begin, and we don't. And so that's okay. All we're going to do is divide the numerator and the denominator and everything in it by 2. So we have r equals, right? Because if you divide the numerator and denominator by 2, it really is keeping an equivalent fraction. So we have 3 halves in our numerator, and in our denominator, 2 divided by 2 is 1 minus, there was really a 1 in front of the cosine. So now there's a 1/2 in front of our cosine. There we go. So here's our equivalent fraction, right? But now we can read E, right? We have a 1 in our denominator to start. And so our E is now next to the cosine. E is 1/2, which means we have an ellipse. Of course, I'm going to have 1 of each, right? Okay, now we need information on the directrix. Okay, here we go. Let's take a look. We have cosine. So again, our directrix is vertical. We have a negative in front of our cosine. So we are left. Oh, is that a plus? Let me go back. I kind of covered it up. It is. Sorry. That's a plus right there. I covered up the part of the plus when I made a circle around the 2. There we go. So let's go back. That was 3 over 2 plus cosine of x, right? And so we have, when we divide it by 2, we have 1 plus 1/2 cosine. I wondered why. I'm like, I thought I would make it a positive to change it up. Okay, so I'm going to erase here. Right. There we go. And the plus means that our vertical line, is to the right of the pole, right? If we had sine in our equation and a horizontal line, we would have been above. Now we just need to know how much. We need to know what P equals. Okay, so let's take a look. Our numerator is 3 halves. And we know the numerator of the formula is E times P. 3 halves equals, and we found E is 1/2 times P. So if you see then that P must be equal to 3 for this to be true, right? I don't know why I put a 4 there, doing all kinds of interesting things. There we go. Let's try this again. So our P is equal to 3. There we go. Okay, let's see if I can straighten that back out. Our directrix is vertical because of the cosine. It is right because of the plus sign, and P equals 3 because of the math we did in the numerator. All right, I was doing silly things. No one was here to stop me, right? Usually in class, I say, have I done anything silly in the last 15 seconds? And it's just me here and the cat doesn't know how to stop me. So let's graph some points. 0, pi over 2 for our theta measure, right? We're getting our chart together. Pi and 3 pi over 2. Before I get my chart going, I'm going to make my directrix. It is from the pole. It is vertical, right 3. 1, 2, 3. There we go. Let's get our angle measures here. Using our angle measures, let's get our radius. You can either use the formula we wrote by dividing by 2, or you can use the original. Either way, you'll get the same answer. I'm going to use the original just because there's not as many fractions. So when I put a 0 in, cosine of 0 is 1. 2 plus 1 in the denominator is 3. 3 divided by 3 is 1. When I put a pi over 2 in for cosine of pi over 2 is 0, and that would be 3/2. Cosine of pi is a -1, and 2 plus a -1 is a 1. 3 divided by 1 is 3. And 3 pi over 2, again, would get us a 3/2. Let's go ahead and graph these points. We have a radian measure of 0 and a radius of 1. There we go. At pi over 2, we have a radius of 3/2. So I'm going to rotate pi over 2, and I have a radius of 3/2. There we go. At a pi, we have the polar point 3 comma pi. So I'll rotate pi and go out 3. 1, 2, 3. There we go. And 3 pi over 2, I'll rotate 3 pi over 2 and go 3/2. And here is my ellipse. There we go. Isn't it fun? I think it's fun. Our last graph, of course, is going to end up being a hyperbola. All right. Notice that we have a 1 in our denominator, and that means that our e next to sine is 2. This means we have a hyperbola. Excellent. Let's get our directrix. Notice because we have sine that the directrix is horizontal. Notice because we have a plus sign in the denominator, it will be above the pole. And now we just need to know by how much. What is P? Okay, let's use that numerator. 3 equals E times P. Our E is 2. Right, we'll divide by 2. And our P is 3/2. You can use a decimal, of course. All right, let's make that directrix. Here's our pole, and it is horizontal above by 3/2, so 1.5. So I'm going to make that horizontal line. As if there's an XY plane over that. Excellent. Okay, now let's go ahead and get our points going. Here's our theta and our radius. Let's do 0 radians, pi over 2, pi, and 3 pi over 2. Okay, when we put in 0 radians, sine of 0 is 0. And so we have, when we do our math in the fraction, a 3, a radius of 3. At pi over 2, sine is 1. And so when we do our math, we have 3 divided by 3, which is 1. Sine of pi is 0, so we have a 3 again. Right, and then at 3 pi over 2, sine of 3 pi over 2 is a -1. So we have a -2 plus 1 in the denominator, and we get a -3. Okay, let's graph these polar points, right? So 0 radians and 3, 1, 2, 3 would be right here. Pi over 2 and 1, let's rotate pi, radius of 1. Let's rotate pi in a radius of 3. There we go. And then 3 pi over 2, this is interesting. We have a radius of -3. So we're going to rotate 3 pi over 2, but rather than go out 3 for the radii, we will go in the opposite direction, as you remember, graphing polar points. 1, 2, 1, 2, and 3. Okay, so how do we draw the hyperbola? Here's what's happening. Look below the directrix. There are 3 points, and our points go through these branches. It was supposed to go through that point. There we go. Now, above, you could use pi over 3 or 2 pi over 3 to get more points above the directrix, because you only have 1 point, which is a vertex. But we also know, due to symmetry with the directrix, that the branch above is symmetric over the directrix to the branch below. So you don't really need more points. All right, let's go on. Now, what if you are given information and asked to write a polar equation on D? So let's take a look at that. Let's write our polar equation. Right, we need R equals E times P over 1 plus or minus E, and then we'll have cosine or sine of theta. Okay, let's get our information. It is a parabola, so our E is 1. So we'll have a 1 here and a 1 here. The directrix is y equals -4. Notice y equals is horizontal, so we will choose sine. Notice that y equals -4 is below, that line is below the pole. So we will choose negative, and our P is 4. Because this directrix, y equals -4, is 4 away from the pole. There we go. Here's our equation. E times P in the numerator is 4. And we have 1 minus 1, which is E, so I don't really need to show it, times sine of theta. And that is the equation for your parabola. Let's write an equation for a hyperbola. So let's do the same thing again. R equals E times P, 1 plus or minus E cosine or sine theta. Okay, let's collect our clues. Okay, E is 3/2. Excellent. We'll be putting a 3/2 here and here. Good. The directrix is x equals -1. Because that line is vertical, we will choose cosine. Because x equals -1 is to the left of the pole, we will choose negative, and the distance the directrix is from the pole is 1. Let's fill in our equation. R equals, E times P is 3/2 times 1 is 3/2. And we have 1 minus E is 3/2 cosine of theta. So this is perfectly true, but you'll see they don't really keep fractions in the numerator and denominator. So I am going to multiply the numerator by 2 and the denominator by 2 to get rid of the fractions. And our final answer is we have a 3 in the numerator And we will distribute the 2 to both terms in the denominator, and we get 2 minus 3 cosine of theta. And there is your final polar equation that you wrote for this hyperbola. So that is our last section for chapter 10. And you just brought everything together. And this is pretty tough stuff you've been doing, so you should be proud of yourself. Have a great day.